When we have a sequence of the form some constant and then exponent n, this is called a geometric sequence. R is called the common ratio. So for example, if we have a sequence like 1.2 to the n, the common ratio is 1.2. If we have a sequence like 1.5 to the n, then this is a geometric sequence with common ratio 1.5 and so on. And now we'll look at why this is equal to infinity. So here's the geometric sequence. When n is 1, we get 1.2 to the first, which is 1.2. When n is 2, we get 1.2 to the second, which is 1.44. When n is 3, we get 1.2 to the third, which is 1.728. And then this is what it looks like all the way up to exponent of 100. So we can see that as n gets larger, the values of the sequence also gets larger. And so that's how we know that as n gets larger and larger and larger, the values of the sequence here will also get larger and larger and larger. And therefore the limit of the sequence 1.2 to the n approaches infinity as n approaches infinity. And here's the geometric sequence of 1.5 to the r, of 1.5 to the n. So when n is 1, we get 1.5 to the first, which is 1.5. When n is 2, we get 1.5 to the second, which is 2.25, and so on. And then we can see here that as n increases, the values of the sequence also increases, also gets larger. And as we can see here, when n is 100, the value of the term a sub 100 is a very, very large number. And so as n gets larger and larger, or as n approaches infinity, the sequence will approach infinity also. And so if r, the common ratio, it is larger than 1, it is greater than 1, then the limit of the sequence will go to infinity. So anytime we have a geometric sequence and r, the common ratio, is greater than 1, then as n gets larger and larger and larger, and then r sub n will go to infinity. Then the next, if we have the case where r is 1, and then in the place of r we have 1, 1 to the n is just 1, and the limit of the constant 1 is 1. So when r is 1, the limit of r to the n is just 1. And now let's look at the case where r is between -1 and 1. So, and then let's look at the simulation program, and we'll see why this goes to 0. And here are the terms for the sequence 0.8 to the n. So here the common ratio is 0.8. So when n is 1, we get 0.8 to the first, which is 0.8. When n is 2, we get 0.8 to the second, which is 0.64. When n is 3, we get 0.8 to the third, which is 0.512. And then here's the rest of it. As well as we can see that as n gets larger, we're beginning to get the 0 here. So here's when n is the 100. N is 100, and we see that we get many zeros here. And that's why as n gets larger and larger and larger, the sequence here, the limit of the sequence, will go to 0. And if we let r, the common ratio, be any number between -1 and 1, then the limit of the sequence will go to 0. So anytime the common ratio is between -1 and 1, the limit of r sub n, as n runs to infinity, will be 0. Now let's look at the case where r is -1. So if r is -1, then the first term will be -1, and then the next term will be 1, because it's 1 square. So it'll be -1 to the first, -1 squared, which is 1, -1 to the third, which is -1, -1 to the fourth, which is 1. So the sequence, we're just going to oscillate between -1 and 1, -1 and 1. And so it's not converging to any number. And so we say that the sequence diverges because it's going to oscillate between -1 and 1. And then the last case, let's look at the case where r is less than -1. And so let's run the simulation program for r of -1.2. So here we have the geometric sequence of -1.2 to the n. When n is 1, we get -1.2 to the first, which is -1.2. When n is 2, we get -1.2 to the second, which is +1.44. When n is 3, we get -1.2 to the third, which is negative. So the sequence is going to go negative, positive, negative, positive, negative, positive. And here's the rest of it. But notice that in terms of absolute value, it's getting larger and larger and larger. So we can see that the value are getting larger and larger, but it's going to alternate between positive, negative, positive, negative, positive, negative. And therefore, we cannot say that the limit of r sub n is equal to positive infinity or negative infinity, because the values of the sequence alternates between positive, negative, positive, negative. So we just say that the limit of the sequence just diverges. And so anytime the common ratio is less than -1, the limit of the sequence diverges. And so here's the summary. For the geometric sequence r to the n is equal to infinity if r is greater than 1, is equal to 1 if r is 1, is equal to 0 if r is between -1 and 1. And then if r is equal to -1, the limit of the sequence diverges. And then if it's equal to, if it's less than -1, then the sequence also the limit of the sequence also diverges. So we have just looked at the geometric sequence. Now let's look at the geometric series. So we have an infinite series like this. when n starts at 0 and goes out and goes to infinity and go to infinity from 0 to infinity. And so the first term will be a to the r, a times r to the 0, which is just a. And then the next term is a times r to the first, a times r to the second, and so on. And the claim is that this infinite series, or this geometric series, it converges and has the sum of a divided by 1 minus r. A is the first term, r is the common ratio, if r is between negative 1 and 1. And this geometric series diverges if r is greater than 1, or if r is less than or equal to negative 1. If r is greater than or equal to 1, or if r is less than or equal to negative 1, and then this geometric series right here diverges. And so the proof is like this. So we let S of n be a be the sum here, a times r to the 0, a times r to the first, a times r to the second, and so on. And then now multiply both sides by r. And so we multiply everything here by r. So this is a now r to the 0 just 1, and so we just get 1, and then this is r to the first. So we get r times a times r, and then a times r squared, and then r times the last term will be a times r to the n. And now we'll do S of n minus r S of n. So we're going to do all of this minus all of this. And when we do that, then we get the first term. This term will cancel out with this term. This term will cancel out with this term. And then this term will cancel out with this term. So we only get the first and the last. So we get a times r to the 0, which is just a, minus a times r to the n. Remember that a is the first term of the sequence. Common factor a, so we get a times 1 minus r to the n. And then common factor here is S of n times 1 minus r. And now divide both sides by 1 minus r. Divide the left side by 1 minus r. Divide the right side by 1 minus r. And we end up with a times 1 minus r to the n dividing by 1 minus r. And then we can rewrite it like this. Now, earlier when we did the analysis of the geometric sequence, we know that r sub n goes to infinity if r is greater than 1. And we know that it's 1 if its r is equal to 1, and r sub n is equal to 0 if it's negative 1, if r is between negative 1 and 1. And then when r is equal to negative 1 or less than negative 1, the r sub n, the sequence r sub n diverges. And therefore, if r is between negative 1 and 1, this part, the r sub n piece, will go to 0. 1 minus 0 is 1, and what's left is just a divided by 1 minus r. And therefore, the geometric series converges to a divided by 1 minus r if r is between negative 1 and 1. And if r is outside of negative 1 and 1, then the geometric series diverges. And now let's look at some examples. Here we have the geometric sequence of 0.4 to the n, which is just 0.4 to the 0 because n starts at 0. It's 0.4 to the first, 0.4 to the second, and so on. A is the first term, which is 0.4 to the 0, which is 1. R is the common ratio, which is 0.4. So R in this case, 0.4, is between -1 and 1. And therefore this geometric series converges or equal to A divided by 1 minus R. A is 1 minus R, or 1 minus 0.4, and we get 5/3. And so the geometric series right here, this is equal to 5/3. Here we have a geometric series, and we get 1.4 to the 0 because n starts at 0, 1.4 to the first, 1.4 to the second, and so on. So the first term is 1.4 to the 0, which is 1. The common ratio is 1.4. Since the common ratio R is greater than 1, the series, the geometric series 1.4 to the n diverges, and in fact the series here is equal to infinity. Here we have the geometric series 1 to the n, which is 1 to the 0, 1 to the first, 1 to the second, and so on. So the first term is 1 to the 0, which is 1. The common ratio is 1. But if we look at the infinite series, this is 1 to the 0, 1 to the first, 1 to the second. So it just means it's 1 plus 1 plus 1 plus 1 forever, which is infinity. And therefore the series here diverges. And so the geometric series of with the 1 to the n diverges. Here we have the geometric series with common ratio of -1. And so the terms here, this be 1, this is -1, this is 1, and then the next term is -1. And so we look at the series here. If we add the first two terms together, we get 0. At the next term, we get 1. At the next term, we get 0. At the next term, we get 1. At the next term, we get 0. And so the infinite series here is just going to oscillate between 1, 0, 1, 0, 1, 0, 1, 0. And so we say that it diverges. It's not converging to any real number. And then here we have -1.4, -1.4 to the n. And so the first term is the -1.4 to the 0, which is 1.4. The common ratio is -1.4. In this case, the common ratio is less than -1, and therefore the infinite series of -1.4 to the n diverges. And again, right here, we don't know if this is equal to, we cannot say this is equal to infinity or negative infinity, because the values of the sequence gets larger and larger, but it alternates between negative, infinity, and negative and positive. Therefore, we just said that it diverges.